Add nothing but positive numbers forever and the answer is negative? Today we dissect the most famous lie in mathematics. Let's start with a single equation. One that has bewitched mathematicians and physicists alike for over a century. 1 plus 2 plus 3 plus 4. Add every natural number all the way out and you get minus 1/12. Something looks wrong, doesn't it? The left side adds nothing but positive integers without end. Yet the right side is less than 1 negative and a fraction no less. It looks like a scam. But this is no internet hoax. Over a century ago, this equation was actually written in Ramanujan's notebook. The value also lives at the very heart of the Riemann zeta function, that towering peak of number theory. Above all, physicists use this number to compute forces that are actually measured. Even when string theory pins the dimensions of the universe at 26, this value is running inside the engine. So the real question isn't whether it's true or false. It's in what sense is it true and in what sense is it a lie? By the end of this video, you'll see that the frowning mathematician and the nodding physicist are both right. This story is a sequel to our last video on the Chasaro mean. Haven't seen it? That's perfectly fine. Before we learn the magic trick, let's get the honest calculation straight. There's no way to add infinitely many numbers all at once, so mathematics uses partial sums. Add just the first few terms and you get a partial sum. Whatever value those approach is the answer to the infinite sum. The formula young Gauss famously used to add 1 through 100 in a flash writes the partial sum neatly. It's n times the quantity n plus 1, all divided by 2. When n is 100 you get 50/50. When n is 1000, 500,500. Let's nail it down with a picture. On the left, the partial sums bolt upward. They eventually overtake any number you name. On the right, the first 6 steps. 1, 3, 6, 10, 15, 21. Growing and always positive. Yet our protagonist minus 1/12 sits below even the very first step drawn beneath 0. As long as we add honestly, the answer is simply infinity. There's no sign of settling at minus 1/12. The answer comes in 2 flavors. A tempting sleight of hand that isn't rigorous, and a real machine that actually explains it. Let's watch the sleight of hand first, the very calculation that made this value famous on the internet. We need 2 ingredient series. First, 1 minus 1 plus 1 minus 1, repeated forever, equals 1/2. Second, 1 minus 2 plus 3 minus 4 equals 1/4. These are the values we earned last time in the sense of averages. We give the somewhere after a name, see. Now subtract ingredient 2 from it, term by term, positions aligned. 1 minus 1 is 0. 2 minus negative 2 is 4. 3 minus 3 is 0. 4 minus negative 4 is 8. What's left is 4 plus 8 plus 12. Every term a multiple of 4, so it's 4c. So c minus 1/4 equals 4c. Rearranging, 3c is minus 1/4. And c lands exactly on minus 1/12. Like magic. Except, this is cheating. This calculation treats a runaway infinite sum like an ordinary number, shifting it, grouping it, subtracting term by term. Those moves are allowed for convergent sums, but a divergent series has no such rights. With a divergent series, merely reordering the terms changes the answer. It even has a name, the Riemann rearrangement theorem. So that calculation is a handy mnemonic, not a proof. And yet the answer is exactly right. Why? Because every step of the trick is secretly a shadow of one deeper object. Time to go meet it. The key is a surprisingly modest idea. A formula born on one home turf can be carried beyond it. A familiar example is the geometric series. 1 plus x squared on forever equals 1 over 1 minus x. But the infinite sum on the left only makes sense for x between minus 1 and 1, inside its home turf of convergence. The formula on the right, though, gives a perfectly good value everywhere, except the single point x equals 1. Off the turf, plug in x equals 2. The left side becomes 1 plus 2 plus 4 plus 8, a runaway sum. Yet the formula answers unfazed 1 over 1 minus 2, that is minus 1. Left panel. On home turf, the partial sums gather at a point. Off turf, they run away. On the right, the purple formula curve extends smoothly off the turf, handing us -1 at x equals 2. This is analytic continuation, extending a formula beyond its home turf of convergence. A deep theorem of complex analysis guarantees it. The smooth extension is essentially unique. We accept the value of that unique extension as the value off turf. Now it's time to apply this to our sum. When mathematicians handle the sum of all natural numbers, this is the formula they reach for, the Riemann zeta function. The definition is friendly: 1 over 1 to the s plus 1 over 2 to the s plus 1 over 3 to the s. Forever. For s greater than 1, it converges nicely, genuine addition anyone can trust. A famous example is Euler's Basel problem. At s equals 2, the sum is exactly pi squared over 6. The trouble is s at 1 or below. The sum runs away, yet zeta 2 extends smoothly across the whole plane, except the single point s equals 1. Riemann accomplished this extension in 1859, in the very paper where the Riemann hypothesis was born. This gluing happens on the two-dimensional complex plane. You don't smash through the wall at infinity, you detour around it. Now the decisive moment. Into the extended zeta, let's plug s equals -1. Formally expanded, 1 over 2 to the -1 is just 2. So it reads 1 plus 2 plus 3 our very sum. And the value the extended function hands us? Exactly -1/12. Look at this curve. The blue stretch on the right is the territory of ordinary addition. At s equals 2 sits our trusty pi squared over 6. At s equals 1, a wall soaring to infinity, the purple stretch on the left holds the values created by analytic continuation. At s equals 0 -1/2, at -3 1 over 120, and at -1 our protagonist. Here the equals sign doesn't mean add the terms one by one. It means the value assigned by the unique extension. A bonus. This explains why the illegal trick of part 2 got the right answer. Meet zeta's sibling, the eta function. The two are bound tightly by this identity. Plug in s equals -1 and eta formally reads 1 minus 2 plus 3 minus 4, our ingredient 2 from before. The right side is -3 times -1/12, that is 1/4. A perfect match. The trick in part 2 was unknowingly imitating this identity, which is why, though the route broke the rules, it arrived at the same destination. Where the mathematician takes analytic continuation, the physicist arrives at the same place by a more hands-on road. They run into this sum while adding up the zero-point energy of the vacuum. Raw, of course, it's infinite. So they get clever, multiply by a damping factor, e to the minus epsilon n, that smoothly trims the terms. The farther out, the harder the trim. The damp sum splits into two pieces, 1 over epsilon squared and -1/12. Send epsilon to 0 and the first piece blows up. But the second piece remains no matter how you do the trimming. See for yourself. On the left, as epsilon shrinks, the terms survive farther out and the total grows without bound. But on the right, subtract off the part that grows without bound, and the remaining shadow always gathers at -1/12. The numbers confirm it. Whether epsilon is 0.5 or 0.02, the shadow settles around -0.0833. In physics, the soaring infinity cancels against an unobservable quantity. Only the shadow survives. This is the Casimir effect, a tiny attraction between two uncharged metal plates held close together in a vacuum. Predicted in 1948, confirmed by experiment in the 1990s. In the simplest one-dimensional model, this -1/12 appears in the raw. For real three-dimensional parallel plates, a cousin from the same family is used, zeta of -3. The philosophy is identical. Subtract the infinity, and the shadow that remains becomes a force you can actually measure. Going one step further, the calculation by which bosonic string theory pins the dimensions at 26 leans on this sum too. 26 minus 2 is 24, twice 12. The 10 dimensions you usually hear about belong to the more refined superstring. The stage for -1/12 is the 26-dimensional bosonic string. Time for an honest reckoning. The answer fits in one sentence. It depends on how you read the equals sign. In the ordinary sense, add the terms one by one forever, the equation is false. The sum runs off to infinity. But in the extended sense, analytic continuation, zeta regularization, Ramanujan summation, the value attached is exactly -1/12. Decisively, three machines with utterly different starting points all point to the same value. That agreement is the strongest evidence of all. What Ramanujan did also becomes clear. Ramanujan summation is not a plain sum. It's a way of peeling off the growing part and reading the finite fingerprint left behind, the constant term of the Euler-Maclaurin formula. January 1913. An unknown young man in India sends his first letter to Hardy, the great mathematician at Cambridge. Among its stunning formulas offered without proof was this equation. When Hardy demanded proof, the reply read, "If I tell you this, you will at once point out to me the lunatic asylum as my goal." He himself knew better than anyone exactly how it sounded. One more bonus. At negative integers, zeta's values follow this formula built from the Bernoulli numbers. Set n to 1, b2 is 1/6. Divide by 2, attach a minus sign, and you get -1/12. Ramanujan's constant term flows from the same Bernoulli numbers. Not a coincidence. A value with a lineage. The most honest notation avoids the bare equals sign, because this value is not the limit of partial sums. The number is real, the equals sign is on loan. We set out from grade school edition, passed through Riemann's number theory, and arrived at forces between metal plates and the dimensions of string theory. And all of it hung on this one small negative fraction. One lesson. In mathematics, the word sum has more than one meaning. Each is honest within its own rules, and where their territories overlap, they never once disagree. -1/12 answers a deeper question, and remarkably, that's the question the universe asks. Casimir's plates are the proof. If anyone asks, tell them. Add the ordinary way, and it's infinity. But read the fingerprint behind the infinity, and it's exactly -1/12. That one sentence holds Ramanujan's letter, Riemann's curve, and Casimir's plates. Thank you for joining me. If you enjoyed today's video, please subscribe, like, and turn on notifications. See you in the next story.